Our next topic generally has a pretty deceiving name. A lot of times you'll hear textbooks and professors and instructors say, we're going to talk about area under a curve, which kind of doesn't make sense at all from the original question. If you think about, we have some curve here, let's call this the function f, and we want to find the area under the curve from A to B, kind of the area under here. Well, technically, that goes down forever. Right, so the area beneath the curve should always be infinite because there's an infinite amount. It goes down absolutely forever here. The questions actually are, the statement's worded wrong from the beginning. We're not actually finding the area beneath the curve. What we're actually finding is the area between the curve and the x-axis. So this is really the area between the curve and the x-axis. So if you ever hear anybody say we're finding the area under the curve, that's actually what they mean, the area between the curve and the x-axis. So a little bit confusing there from the start, but the good news is we can actually use our newfound skills to help us, and using what's called the first spelling here. Theorem of Calculus. The first fundamental theorem of calculus says this. We're going to take our integral here and we're going to add bounds on it. So when we add numbers to the ends of an integral, we say that those are bounds, and we'll get to that in a second. If we integrate this, the good news is we get the same thing when we integrate it. Our integration rules do not change. But now we're going to need another symbol here that you may or may not have seen before. It's a straight up down bar, and we're going to have a number at the bottom and a number at the top. These are still called bounds here. Now what this is telling you to do, anytime you see something like this, it says plug in the top number minus, then plug in the bottom number. So this will be big F at B minus big F at A. Okay, when you have bounds on an integral, it's called a definite integral. With bounds, it's called a definite integral. So guess what? The integrals that we've seen before that didn't have bounds on there are called indefinite integrals. So if it has bounds, it's called a definite integral, which means you need to evaluate the integral or the antiderivative at the top endpoint minus the bottom endpoint. Now, this is what the first fundamental theorem of calculus says, but believe it or not, what this actually gives us, this does give us the area between the curve and the x-axis from A to B. So this integral represents, if you have some function here, little f, now notice that's little f, from A to B, it gives us that area right there. That's what this represents. Okay, so like I said, the good news is our integration is going to be exactly the same. We're just going to have a little bit of arithmetic to do after this. So let's just try an example to see how this works and see how the notation goes. And then we got a few more things that we got to talk about. So let's just say if I say, what is the integral from 0 to 1 x squared dx? Well, according to this, we need to integrate our function and then evaluate it from the top endpoint minus the bottom endpoint. So our first step has nothing to do with those bounds. So to integrate this, we know how to integrate x squared, that's just x to a power. We add 1 to the power and divide by that power, and we need to evaluate that from 0 to 1. Now, hopefully a couple of you just said, hey, Mr. Bentley, you just forgot the plus c. And I did and I didn't. I'll show you here in a second. All right, so now what do? We plug in the top endpoint. So when I plug in the top endpoint, I get 1 cubed over 3, minus when I plug in the bottom endpoint, I get 0 cubed over 3. So this is 1/3 over 3 minus 0, which is 1/3. So if you were to take a look at the picture of x squared, That was our original function, right? X squared. And you look at the area from 0 over here to 1, the area of kind of that somewhat triangular region right there would be 1/3. 1/3 what's? I don't know. We don't know what the units are. 1/3 feet squared, miles squared, meters squared, who knows? All right, now for those of you that were thinking that I forgot the plus c when I integrated, like I said, you're both right and wrong. I didn't actually forget it. Let's do this. Watch what happens when I integrate this. What if I had put the plus c there? Now I want to integrate from 0 to 1. Well, the same type of thing would have happened here. I would have got 1 cubed over 3 plus c minus 0 cubed over 3 plus c. So that would be 1/3 plus c minus, well, that's 0, c. 1/3 plus c minus c, which is just 1/3. Right, you see that if we had the plus c here, this one's always going to have a plus c with it, minus this one's always going to have the same plus c. So whatever that c is always going to cancel. Now, do you actually get the plus c when you integrate? Yes. Yes, you actually do. But when you have bounds, that c is always going to cancel, so just save yourself a little time and you don't have to write it. If you want to make sure that you don't forget, you can always put it in there, but it will always, always, always cancel. All right, let's just try another example here. What if I said, what's the integral from 1 to 2 x squared, let's do this a little different. Let's do 4x cubed minus 2x. So this will be a little bit more difficult. But again, we have bounds, so this is called a definite integral. So first thing we need to do is just integrate it like we normally would. So here we're going to add 1 to the power, divide by that power. On this one, we're going to add 1 to the power, divide by that power. We still need to evaluate that from 1 to 2. I'm going to go ahead and reduce this first. This is x to the 4th minus x squared evaluated from 1 to 2. Make sure you're using parentheses at this next step. When you plug in the top endpoints, you get 2 to the 4th minus 2 squared minus, then when you plug in the bottom endpoint, that's 1 to the 4th minus 1 squared. So this is going to be 16 minus 4 minus 1 minus 1. So 12 minus 0, which would be 12. Okay, so there you go. So you notice the only thing that we've added by adding a definite integral is we have some arithmetic to do at the end. Our integration is exactly the same. All right, let's try another one where we're actually going to end up with something that's a little weird. Get this out of here. So let's just say the directions, same thing we've been doing. The directions for something like this would say evaluate. What if I gave you something simple like -1 to 1 x cubed dx? So do me a favor, hit pause and go see if you can evaluate this definite integral. You back? All right, if you're back, let's give this a shot. So when we integrate this, we add 1 to the power, that's x to the 4th, divide by that power, we get 1/4, that you can just divide by 4. Evaluate it from -1 to 1. So when we put -1 in there, that's -1 to the 4th minus 1/4, 1 to the 4th. So -1 to the 4th is positive 1, so this is just 1/4, and 1 to the 4th is 1/4. 1/4 minus 1/4 is 0. All right, by the way, if you got 0, great job. You did it perfectly. However, you should be asking yourself right now, Mr. Bentley, didn't you just say that this represented area? And I did. Then how can you have 0 area unless it's actually the curve, right? I mean, we're talking about the area between the curve and the x-axis. The only way there would be no area if our curve was exactly the x-axis. That's not the x-axis. That's something that looks like something like that, right? So there definitely should be area between the curve and the x-axis. So why did we get 0? Well, it's kind of a little bit in the wording. Now remember, we're integrating from -1 to +1. If you take a look at the areas in these regions, on the right-hand side, this is the area between the curve and the x-axis. However, on this side, this is the area between the x-axis and the curve. That's backwards, isn't it? So what actually ends up happening here is this area right here, because it's below the x-axis, because it's backwards basically, we actually get a negative area for this, and that shows up kind of this piece here. Right, you see how we had a negative piece? I'll show you in a second. Now this piece over here, since this is the area between the curve and the x-axis, that would actually be positive. But visually you can see that they're the exact same size, so this positive area was canceled out by that negative area. Now I know it's weird when you say negative area because there's no such thing as negative area. We call it negative area because we just say that means it's area below the x-axis, which runs us into a few problems that we're going to see in the future. Here's the good news. If the directions just say evaluate, it says find the value of this integral, which is 0. However, if the directions said find the area between the curve and the x-axis, the answer is not 0 here. It's actually a half. So we'd have to do some extra work for that. All right, so for our definite integral though, good news is our integration rules are exactly the same. Once you integrate, you're going to evaluate at the top endpoint minus the bottom endpoint, so you should always have two pieces here, and end up with a finite value. Now that value generally represents the area between the curve and the x-axis, unless the curve drops below the x-axis, and then it doesn't actually represent area as we generally think about it. However, most of your instructions generally should be just evaluate, which means just do the integral, evaluate the top endpoint minus the bottom endpoint, and that should be your answer.